Hello and welcome to this NPTEL course titled Quantitative Methods in Chemistry. My name is Ashish Srivastav and I will be the instructor for this course for the next few weeks. So, this is week 4 of the course, and this week we will be learning about hypothesis validation, what is null hypothesis, what are confidence levels, confidence intervals, what are two-tailed test, one-tailed test, and use of statistical tables such as Z table, T table, F table, etc. for analyzing scientific data. So, the objectives for this week's course are to define the concept of hypothesis and compare and contrast the available statistical tools to develop and verify various hypotheses. So, let us begin this week's classes. So, this week we will understand how statistical tools can be employed to analyze scientific data and arrive at an unbiased conclusion. Usually we will have a hypothesis that we will propose, and then we will conduct experiments to test our hypothesis. These experiments will generate a set of data, and when we analyze this data through a variety of tools, we understand what this data is telling us, and then we derive at a inference from what this data is telling us. However, before we move further, it is important to delve in what the term hypothesis itself means. If we go by the dictionary meaning, it is a supposition or a proposed explanation based on our limited evidence, which acts as a starting point for further investigation. It is also important to emphasize that it is a proposition without any assumption of its truth. So, a hypothesis needs to be tested for its truthfulness, and we need to test this hypothesis and arrive at a conclusion that is not influenced by our personal beliefs and biases. And how do we do this? Before that, let us see some example of hypotheses that are testable or that we can test through generation of scientific data. For example, let us presume that we created a treatment for a certain illness. Now, we need to test whether this treatment is actually working on the disease that we are utilizing this treatment for. To test that, we will propose the hypothesis that the new treatment is significantly better than the previous one in treating the disease. However, as is written here, this hypothesis may or may not be true, and we need to test this hypothesis for its truthfulness. Another example is the water or the air quality of the city has deteriorated in the last few years. Now, we do not know whether this is true or false, and again this is a hypothesis which is testable through generation of scientific data. Another example of the same concept is, let us take a student X who is enrolled in course 1, and we want to test whether the student X has better academic credentials than the student Y who is enrolled in a different course which we call as course 2. So, again the fact that student X is having better academic credentials than student Y may or may not be true, and this again becomes a testable hypothesis. Now, when we are testing our hypothesis, we as human beings, this includes researchers and scientists like us, we are prone to our own personal biases. And the question that we have in our hand today is, how do we remove our biases while drawing inferences from scientific data? And the answer to that is, we employ statistics for doing this. Statistics provide us with scientific tools to analyze the data and test our hypothesis in an unbiased manner. So before we delve further, let us take a very quick recap of what the statistical terms that have been introduced in this course. One of the terms that you might have encountered is the concept of population. In statistics, population is the collection of all the data points or measurements that are of interest to us. And when we say all, we mean actually all. For example, when we are talking about progression of disease, we say that all the cells that are involved in a particular type of disease. Similarly, it can be all the items that a particular company is producing, or all the citizens of a country or a city or a state. And in nutshell, a population contains complete information necessary to make inferences that, however, when we start analyzing the whole population, this can be too tedious or often impractical to analyze. So what is the solution? The solution is that we take a small subset from the population and make our inferences for the whole population. Now this subset is known as the sample. So to rephrase, a sample is a subset of the population from which we will derive inferences about the population. It provides an approximate information or an indication about the population that we are dealing with. It does not contain the complete information about the population. However, analyzing a smaller sample is more convenient. Now, the same concept can be understood by use of the Venn diagrams. For example, this circle which we have drawn here indicates a set of data points which we will call as the population. Now, as told before, analyzing this whole population may be too tedious, so we will utilize a small subset from this population which we will call the sample, and we would utilize the information contained in this sample to make inferences about the whole population. Another point that has been emphasized in this course is that when we collect a large set of data and we collect it in a random manner, that means we do not put our own influences or biases into it, this data will follow a Gaussian distribution. So it would be distributed symmetrically around the mean value which we indicate by mu. For example, this profile which we have drawn here is what is known as a Gaussian profile. Now, as we can see very clearly, the data points are distributed quite evenly across the central point, which is the mean value of this data set. So when we plot the frequency of occurrence versus the observed values, we get this Gaussian profile. From this Gaussian profile, it becomes easy to analyze the data through mathematical formulae. For example, we can easily figure out what is the mean value of this data set. Similarly, the spread of this data set is given by what is known as the population standard deviation, or sigma. Now, the sigma is given by a mathematical formula which looks something like this. So xi is the individual values of this data set, mu is the mean value of the data set, and n is the number of points in the data set. So, if we have the information about mu and sigma, we can very well understand how this population of data is behaving. Now, we have also told that from a population we can take a small sample which is considered as an approximation of the population if it is taken in a random fashion, and this sample can also be analyzed using statistics to arrive at similar concepts of sample mean, which now we denote by x bar, which again is a summation of all the individual values divided by the number of values present in the sample. Similarly, we can have a sample standard deviation now, which is denoted by S and is given by the formula written on the board. So, here the numerator is nothing but what we call as the deviation squared, and n minus 1 value comes from the fact that for small samples we use the degrees of freedom. So, essentially the sample standard deviation boils down to the square root of the deviation squared divided by the degrees of freedom. This can also be written as the formula shown here, and both equation 1 as well as equation 2 will essentially give you the same values of the sample standard deviation. Now, let us look at the equation 2 a little bit more in detail. Equation 2 tells us that we need to take the individual values which are squared and summate all of them and subtract from this summation the individual values summed together and then whole squared, and that divided by the number of observations n, and then this whole thing is being divided by the degrees of freedom. Okay. Now, let us consider a simple example where we are dealing with two different populations. Now, these populations are shown in this slide as the blue profile and the red profile. So, population 1 is denoted in blue while the population 2 is denoted in red, and we have plotted in this graph the frequency of occurrence and the observed values. For example, let us take that these two populations are those of students who are taking two different courses. Okay. So, in these two courses the students have got different marks, their marks distribution is different, and even the mean values of the marks obtained for the two courses are different. For course 1, the mean value is given by mu1, and for course 2, the mean value is given by mu2. Now, the question is, how do we analyze these disjoint set of data and try to arrive at a conclusion whether a particular point is distinctly different from the other? Now, let me delve on it a little bit further. So, what we will do here is, if we look at the observed values profile, these population 1 and population 2 are well separated. Now, how do we bring them together to analyze them together? One simple way to do this is to convert the observed values into the deviation from the mean values, and this deviation is given by the formula di, which is equal to the xi minus mu, and xi are the individual values and mu is the population mean. So, when we do that, the blue and the red profiles or populations now merge around a central point, which is the point at which the deviation value is 0. Now, the deviation can be negative as well as positive, and which is what is clearly shown in this profile. Now, even here we have a slight challenge in the fact that the red profile seems to have a smaller standard deviation compared to the blue profile. So, it may still not be possible for us to analyze these two data together. One further step will help us merge these two data together for an easier analysis, and that is done in the next slide, where we have used what is known as a z statistics, which is the deviation values divided by the standard deviation. So, in other words, the z statistics is nothing but the deviation values in standard deviation units. Again, the values can be, z values can be positive as well as negative, but in this z profile, what we see is that the blue and the red data now merge quite completely over one another. So, if you want to compare point 1 versus on the blue curve versus point 2 on the red curve, it would be easier for us to analyze these two distinct or disjoint set of data. So, when we convert the Gaussian error function in terms of z, it takes the form which is shown here. So, you integrate it from minus z to plus z to get the area under the curve, and it takes the form of e to the power of minus z square by 2 by square root 2 pi. So, if we integrate this, we get the area under the curve. Now, when we do that, what we observe is that based on the z value that we plug in this equation, we get a variety of the area under the curve values. So, for example, if I take the z value from minus 1 to plus 1, then we get the area under the curve being 68.3%. So, which, for example, we can shade like this. So, this area which has been shaded now is 68.3% of all the data points that we are dealing with. Similarly, when we expand this to plus minus 2 z values, then we are able to cover a larger area under the curve, and this corresponds to 95.4% of all the data points that we are dealing with. As we go further, we can make it to z plus minus 3, where we are now able to cover a very large proportion of the area, which is corresponding to 99.7% of all the values. In order to cover 99.9% of all the values, we would have to use a z value of plus minus 3.29. So, as we can see that this profile is very similar to that what we obtain when we plot the error function with respect to the sigma value or the population standard deviation. Now, a few points to recollect here are that this Gaussian error function is coming due to random fluctuations during our measurements, and when we repeat our measurements, if we do that in an unbiased manner, the measurement is supposed to take a Gaussian profile, which is demonstrated here. Now, these fluctuations in our measurements are considered to be natural and beyond our control, and for a Gaussian profile, the frequency of occurrence of a value which is very far from the mean value is very low. So, which is again mentioned here, it diminishes very rapidly as the value that we are measuring moves very far away from the mean value, which is denoted here. Now, this has an important implication in the terms of the z score. So, what we rephrase this statement as is, if we have a higher z score, that indicates that the probability of that reading or that measurement, so probability needs to be highlighted, coming due to random fluctuations is very low, which again we can see in this profile. So, if I have a z value of say plus 3, that it is 99.7% not likely to be coming due to the random fluctuations. So, the probability of this point with a high z score of plus 3 is only 0.3% coming due to random fluctuations in our measurement. That means this data point with a z score of plus 3 is considered to be statistically quite significant.